Hello everybody, welcome back to my Gregorius Maths video. Today we'll be looking at connectivity. So in the last video we looked at a certain type of topological space with the subspace topology and subspaces and whatnot. And the video before that we defined a topological space and gave some examples on Rn and stuff, whatever. So now we've looked at some of the basic topological spaces, and we've looked at the definition of a topological space. Okay, so we have kind of like a brief landscape. We kind of know some of the stuff. Okay, and we know stuff about continuity and whatever in those between those topological spaces. So now I think it will be appropriate if we move on to look at properties of those topological spaces. And today we'll be looking at connectivity. But first let's look at a theorem which topologists like to prove, similar theorems to this. Okay, the theorem states there does not exist a continuous surjective map F from the real numbers to the zero sphere. Okay? Okay. So, let's look at the proof. Let's look at exactly what we have to prove. Okay? So first let's assume that there does exist such a map. Okay? That would imply that the pre-image of -1 is equal to some u, for example, and the pre-image of 1 is equal to v. Okay? Now, seeing as f is continuous, u and v are open, okay, which I'll use later on. Also, seeing as -1 and 1 constitute of the whole of the zero sphere, that's the definition of the zero sphere, the points 1 away from the real line, so just -1 and 1, the origin of the real line, so just -1 and 1, okay? Alright, this also implies that union v is equal to the whole of the real line, and u intersect v is equal to the empty set, seen as 1 and -1 are disjoint, and seen as f is surjective, u and v are not empty. Okay? So now what we have to do is prove that no such what we have to do is to prove that no such sets can exist. Okay? So first, let x be less than y. Okay, so if x is less than y, this means that the closed interval about x, y contains points in u and v, okay? So now let's look at the midpoint. If v contains x plus y over 2, so this is the midpoint, that means that the closed interval about x and x plus y over 2 contains points in u and v, okay, if x plus y over 2 is in U, that would imply that there is a closed interval about, that would imply there is a closed interval about x plus y over 2, and y, okay, but either way, okay, so either way, there is a closed interval of length. Okay, so there's a closed interval of length y minus x over 2 such that it contains points in U and V. Okay? So now we can halve that, leaving us with a closed interval of a length y minus x over 4, so we halved the length of the closed interval, contains points in U and V. Okay? And we can continue this. Okay? But when we take the intersection of all of these closed intervals, okay, when we take the intersection, we will get a point z in the real numbers. Okay, so when we take the intersection of all of these closed intervals, we carry on this process of halving the length. Okay, we get a single point z in the real numbers. Okay, now let's assume that z is in U. Okay, we'll show that this is not possible. Okay, and then once we've done that, we can use the same argument to show that z can't be in V. Okay, I won't have enough space, but we use the exact same argument. Okay, if z is in U, this implies that there exists some delta z greater than 0, okay, because U is open. By the continuity of F, U is open. Excuse me. Okay? Such that the open interval about z minus delta z to z plus delta z is completely contained inside of U. Okay? And, okay, so there exists a delta z such that z minus delta z, okay, any interval, okay, of a length less than delta z containing z, okay? So any interval of length less than delta z containing z is contained in this open interval, z minus delta z to z plus delta z, okay? But how long can this delta z be? Well, if we have intervals of length y minus x over 2 to the n, okay? Okay, for large enough n, this interval satisfies the condition that it is of length less than delta z contains z, okay? But how large exactly does n have to be? Well, n must be log base 2 of y minus x over delta x. Sorry, delta z. Okay, that should be pretty obvious, right? That's how big n must be. But what do we know about these intervals? That there exists a point in U and V in these intervals, and this is the point at which we have fun, because this implies that U intersect V does not equal the empty set. Okay? Here we have a contradiction, and hence such a map cannot exist. Okay? Now the proof is complete. Okay? But, well, not technically, but we can use the same argument if Z is in V. Okay? And with that, the proof would be complete. Okay? So, let's see exactly what we have proved and why I took the time, why I even bothered to prove this at a start of a video about connectivity. Okay? Why did I take the time to prove something seemingly random? Okay, it was pretty cool. It was a pretty cool theorem to prove, right? It's pretty fun proof. But I mean, what was the point in a video about connectivity, right? That's probably what you're wondering. Well, now I lay down the definition of connectivity, and this should look very familiar to you, having seen that proof. Okay? Well, actually, I'll lay down the definition of disconnectivity. Okay? A topological space T is disconnected if, okay, it satisfies three conditions. If there exist subsets of t, u and v, such that u intersect v is equal to the empty set. Okay, looking familiar kind of. U union v is equal to the whole thing, i.e. u and v cover t, that's also known as covering t. Okay, and u is not equal to the empty set, and v is not equal to the empty set. Look at how familiar that is. Those are all the conditions that we had to satisfy f being continuous and surjective. Okay, if such subsets don't exist, okay, T is connected. Okay, so our first example of course R, the real line, is connected. Okay, that's what the first part of this, the second part of the theorem showed, that no such subsets could exist. Okay, now a surprisingly important lemma, at least for this video, okay, is if T is connected, okay, there cannot exist a continuous, surjective map f from T to the zero sphere. That's also something that we showed. Okay? So we showed two things kind of accidentally from just proving that one statement. Okay? So that was why it was useful to prove that, or to know how to prove it. Okay? So now let's look at the fixed point theorem for the closed interval about 0, 1. Okay? Also, the closed interval about 0, 1 is connected. Okay, and we can just adapt the way that we showed that the real line is connected to this. Okay, I'm pretty sure this works for a closed interval about a, b. But I definitely know this works for the closed interval about 0, 1. Okay? Oh, whoops, I rubbed out connected. Okay, let's look at the fixed point theorem. The fixed point theorem says, okay, if a function f from the closed interval between 0 and 1 to the closed interval between 0 and 1, okay, is continuous, I think, and surjective, okay, then there exists an x such that f of x equals x. Okay, so there is a fixed x. Okay? How do we prove this? Okay? Well, how can we prove this? Well, first of all, we can define g of x, some new function g of x, to equal x minus f of x over the absolute value of x minus f of x. Okay? And this is possible because f of x is never equal to x, okay? Well, if this is not true. Okay, so we're assuming this is not true. Okay? So we can define g of x to be as such. Okay? Now, g of x is continuous because f of x is never equal to x, right? And it's surjective. Okay? So, this g of x maps onto the zero sphere. Now, as f of 0, okay, is not equal to 0, this means that f of 0 must be greater than 0, okay? Because remember, it maps onto the closed interval between 0 and 1, right? Meaning that g of 0 is equal to, well, the top will be negative and the bottom is always positive, so negative 1, okay? And f of 1 is not equal to 1, is not equal to 1, okay, therefore implying that f of 1 is less than 1, therefore g of 1 is equal to x minus, 1 minus something less than 1 is going to be positive. This is always positive. G of 1 is equal to 1. Okay? And now, okay, because g of x maps onto the zero sphere, okay, and it goes from the closed interval between 0 and 1 to the zero sphere, and the zero sphere, and we showed that any map which goes from a connected space to the zero sphere can never be continuous and surjective. This means that G cannot exist okay, hence there exists some f of x equal to x. Okay, so what was the point of these lines? Well, we had to show, we had to show that G was surjective. Okay. Cool. So that was the fixed point theorem, and we can see how useful it is to just not have to prove every time that there cannot exist points u and v such that they satisfy this. Okay? If we just know how to prove the general case, we can just reduce the problem down to proving that our domain is connected instead. Okay? So now let's look at another theorem. Okay? Let's look at the intermediate value theorem. Now we want to show another theorem. So if f takes in a closed interval between a and b and outputs some real numbers, okay, and f of a is greater than 0 and f of b is less than 0, then there is an f of x equal to 0. Okay? This is the intermediate value theorem. Okay? Now how do we proceed to prove it? Well, the proof is as follows. Okay? So, assume that this is not true. Then we can define f bar of x equal to f of x over the absolute value of f of x. Okay? So very similar reasoning to the last proof. The last proof we let g of x equal to whatever, and all we had to do was show there was continuous and surjective, and then it couldn't exist. How we showed it was continuous? Well, because by the assumption that f of x is not equal to 0, or whatever it was in the last theorem. And how to show that it's surjective is that it goes to the zero sphere and it takes all of the points onto the zero sphere. Okay? So let's show that. Well, of course this is continuous because f of x is not equal to 0. Okay? And now seen as f of a, okay, is equal to, well, f of a is greater than 0, so f of a is equal to 1, f of b is equal to -1, okay, we can think of this function as a function f bar goes from the closed interval between a and b to the zero sphere, okay, and by a similar argument as before, this closed interval here is connected, okay, therefore implying that f bar doesn't exist. Okay, now we're seeing just how useful it was that we took the time to prove the first theorem at the start. Okay? And hence, and because f bar cannot exist, this implies that f of x equals, there exists an x such that, okay, there exists of x, that implies that there exists some x such that, yes, x an element of the, fine, I'll write it out, in the closed interval between a and b, such that f of x equals 0. Okay, that's good. Now, the theorem, the lemma which we showed at the start, or near the start, that a function f, which goes from one connected space t to their zero sphere can never be connected, has got, in fact, converse, you stupid child. Okay, so the converse is this. If, I'll just write down the fact this is a lemma. If t is disconnected, okay, there is a continuous surjection, okay, from t to the zero sphere. Okay? The proof is fairly simple, okay? Proof. Since t is disconnected, I'm just going to call it discon for now. Okay? Okay? Since t is disconnected, this implies that there exist subsets of t, u and v, such that u union v is equal to t, okay? U intersect v is equal to the empty set, and u is not equal to the empty set, and v is not equal to the empty set. Okay? Yeah, this one was a mess. Okay? Now all we have to do is define f as follows. F of x equals 1 for x in u. F of x equals -1 for x in v. Okay? Now clearly, f is surjective, okay, and f is continuous, okay. So pretty much right from the definition, this is true, okay. And now, okay, just to finish off, kind of like a is that what they call it, a handicap?
So stupid.
Oh, handicap. I thought that was wrong. A nightcap, sorry, not handicap. Kind of like a nightcap, but like a maths snack, midnight snack. It's nearly midnight, I think it's 11, not sure exactly what the time is. Something late, I should be asleep. Flex. Yeah, okay. This is an hour behind, so it's actually 11:30. Wow, okay. Oh my god, yeah, this is pretty much my nightcap. Okay, so if S is connected and T is disconnected, okay, there does not exist a continuous surjection, okay, from S to T, okay, simply because okay, so there does exist a continuous surjection from T to the zero sphere, okay, if there was a continuous surjection from T to S, okay, that would imply that there is a continuous surjection from S to the zero sphere. Oh, sorry, wrong way around. Whoops. Yeah. Okay. Yeah, this is the right way. Okay. Which is not true. Okay, proof by contradiction again. And glug glug glug. We're finished on Nightcap. Thank you guys for watching. If you watched to the end, hopefully you understand quite how important connectivity is, topology, and how useful it can be to prove stuff like the intermediate value theorem, etc. I hope to see you in my next video, where I shall be discussing compactness. Goodbye.